current phase of the moon, if you went to the beach at Santa Monica and waited for 24 hours, do you know how many high tides you would observe? When you're walking into the Duke Chapel, do you know what direction you're facing? Do you know what time the sun rose this morning here in LA? If you don't know the answer to any of those questions, it may be you're paying more attention to your smartphone than the natural world. Several years ago, I taught a freshman first-year seminar entitled Ancient and Modern Perceptions of Our Natural World. And on that first day, I asked the freshmen that were assembled these very same questions. They did not fare well, except for one student, and she had the perfect answer to the question about when the sun rose. And her answer was, way, way before I did. That was full credit. But not everyone gets up too late to see the sunrise. There have been keen observationalists throughout the millennia who've made very careful observations of our world, and these observations, some of them, have overturned our understanding of this earth. Take Galileo. Using his homemade telescope, his careful observations of the 4 moons rotating around Jupiter shattered the dominant paradigm at the time that all heavenly bodies rotated around the Earth. But you don't have to be a Galileo to observe the changes in precipitation here in Southern California these past few months. Just when you thought it would never rain again, just when you painted your lawns green, the rains returned and returned. Now, I know that you know that El Niño is to blame or thank for this change in fortune. But you may not know that the changes in these local atmospheric conditions are really the result of temperature changes in the tropical waters thousands of miles away from here. Now, tropical waters are always warm. They're always warmer than waters to the north and to the south. Behind me is a map of those sea surface temperatures around the globe. And this uneven heating is not a surprise. It's due to the fact that we get more solar radiation in lower latitudes than higher latitudes. And this uneven heating really sets up our global climate system and the normal patterns of precipitation and drought that we have around the globe. But sometimes the tropical waters are warmer than they are at other times. So we're going to zoom in to the tropical Pacific, and we're going to look at the sea surface temperature anomalies or deviations from the mean this past October. Wherever you see red, the ocean waters are warmer than they are on average, and whenever you see that gray color, they're cooler than they are on average. You see the really strong warming of the tropical ocean waters in the eastern part of that basin and the warm waters off of California. This is the signature of El Niño. It comes about because the ocean and the atmosphere are chaotic fluids. And in that chaotic system, there are perturbations at times that cause a redistribution of the heat. This has been going on for as long as this Earth has had an ocean and an atmosphere, which is a very long time. Now, because the ocean heats the overlying atmosphere, this redistribution of heat means that that atmosphere at times becomes warmer, and when it becomes warmer, then it changes the rain patterns and it changes the wind patterns as well. And because those changes in the tropical Pacific involve a tremendous amount of heat, these changes are felt worldwide, but particularly here in Southern California. El Niño years are warm years around the globe. And for those of us like me that study global climate change, El Niño is somewhat of a bother. I'm interested in how, as a function of time, the temperature slowly changes. But the El Niño creates these large-scale changes that really pollutes that signal in a way. So what do? I go somewhere where the climate signals are unpolluted by El Niño. I study the deep waters in the North Atlantic. Now, to understand why, I'm going to take you back and tell you a story about Count Rumford and take you back to 1751, when a British sea captain was transiting across the Atlantic and stopped to take measurements of the ocean waters from the sea surface down to about 2,000 feet. The captain and his crew, using a bucket with a thermometer made by Mr. Fahrenheit, lowered that bucket, and recorded that the surface temperatures were very warm, but as they got further and further down, the water became colder and colder. Now, the captain and his crew didn't care that much about what this meant to science, but they were very pleased to have found a source of cold water to cool their wines and cool their baths in that vastly disagreeable climate. But 50 years later, Count Rumford stumbled upon these measurements, and he considered them a scientific puzzle. He couldn't figure out how those deep waters got so cold. They were colder than the surface temperature ever was. The surface temperature was not that cold at night, not even that cold in the winter. But Count Rumford figured out that those cold waters at depth in the tropics are there because the ocean waters overturn. In the winter at high latitudes, the surface waters lose their heat to the atmosphere. They become very dense, they sink, and they spread equatorward. They fill the deep ocean with these cold waters, and in time, those waters must upwell and return to those deep water formation sites. This is called the ocean overturning circulation, or popularly called the global conveyor belt. This overturning circulation brings warm water from the tropics up to the high latitudes. It's the reason Iceland is warmer than Greenland. It's the reason the British Isles are colder, are warmer and wetter than comparable latitudes in Canada. But today we have another reason to be interested in the overturning circulation, and that is because today 30% of the carbon dioxide that's been released into the atmosphere since the Industrial Revolution because of the burning of fossil fuels is in our ocean. Let me explain how that's come about. We're going to look at the inset first in the slide behind me, and we're going to imagine that we're on a ship along that red line that leads first from Iceland southward through the Atlantic. We're going to go eastward across the Southern Ocean, and then back north up to the Pacific to the Aleutians. We're going to take that red line, and we're going to measure that as the distance, 0 all the way 30,000 kilometers away is going to be the length of our voyage. Along the way, we've measured the concentration of anthropogenic carbon dioxide in the waters and at different depths. Wherever you see red, there's a high level of carbon dioxide. Wherever you see blue, it's low. And what you see is that in the surface waters everywhere, as expected, we have those high levels of the carbon dioxide. But here in the North Atlantic, we see that the carbon dioxide concentrations are high at depth. That's the overturning circulation in action. That carbon dioxide absorbed at the surface is being brought to depth because of the action of the overturning. This is good news, and this is bad news. It's good news because that carbon dioxide, if it isn't in the ocean, it would be in the atmosphere where we know it would contribute to global warming. It's bad news because that carbon dioxide in the ocean leads to ocean acidification, which is an unhappy prospect for marine ecosystems. What oceanographers want to know is the extent to which the ocean, that deep ocean, will continue to be a carbon reservoir. And that, in turn, depends on how the overturning circulation will change in the years and decades to come. And this is where my work comes in. We understand that as the ocean waters warm, the surface waters at high latitudes will become less dense, less likely to sink. We also understand that as ice melts, the surface waters will also become less dense, less likely to sink. And so our working assumption now is that as we have a warming climate, the overturning circulation will slow because the waters will be less likely to sink. But we don't know that for sure. We don't know by how much, and we certainly don't know when. So colleagues and I decided to go to the high latitudes of the North Atlantic where the waters overturn and measure the temperature and salinity in the overturning circulation itself. Several years ago, I conducted a workshop on the Duke campus and gathered oceanographers around the world to design a new program. And from that workshop at Duke, a new international observing system was launched called OSNAP, or Overturning in the Subpolar North Atlantic. And the idea is to launch an observing system from Labrador over to Greenland and from Greenland over to Scotland. Now, years ago, when we wanted to measure the ocean, we really only had one choice. Oceanographers piled onto a ship that slowly plied its way through the seas. We took measurements of water and recorded those measurements while at sea. Today's a different story. Modern technology allows us to observe the ocean in ways unimaginable to that 18th century sea captain. Today, we can launch floats and gliders from small watercraft. And these autonomous vehicles ply the waters. They move up and down, measuring temperature, salinity, and oxygen. And they pause occasionally at the surface, where they relay their information to a passing satellite, so that an oceanographer can sit at a cozy coffee shop with her laptop and retrieve data from distant parts of the ocean. For oceanographers prone to seasickness, like me, these are a godsend. The observing system is behind me. What you're looking at in color is the salinity of the waters in the northern North Atlantic, and you're looking at the Labrador Basin, the Greenland Basin, and the Scotland Basin. And every place you see a vertical line is where we've been out there and put that mooring in with instruments that will measure the ocean properties and currents. And where you see gray shaded box, there are gliders that we've released. As the international lead for this program, I am enormously proud that this system is in place. There are 7 different countries contributing to this, but it is a US-led effort. Next fall, our first observational measurements will come out, and I'm convinced that the data that we'll collect here will enormously aid our efforts to predict how our Earth's climate is going to be evolved in the years and decades ahead. So all of this matters to Duke because I'm Duke. Whether I'm in the classroom or at sea or standing here in front of you, Duke has afforded me amazing opportunities. The university has fostered my development as a scholar and a teacher, and it's given me great colleagues and students to work with. So because of that support and because of the work of my other colleagues who study the ocean and the atmosphere, Duke is at the forefront of climate change science. Duke is making a difference in this world. Thank you.